Hi, so today we're going to discuss electric potential and potential difference, electric potential and potential energy due to point charges, electric potential due to a continuous charge distribution, electric potential of a charged conductor, capacitance and combining capacitors in series or parallel, energy stored in a charged capacitor, and capacitors with dielectrics. So as we mentioned in the videos of mechanics, forces can be either conservative or non-conservative. And the electric force is a conservative force, and therefore it can be described in terms of electric potential energy, okay? And as we have seen in mechanics, this can really simplify solving problems since instead of dealing with forces which are vectors, we can use energy, which is a scalar, and easier to handle in solving problems, okay? So if a test charge Q naught is placed in the vicinity of an electric field E, the electric force acting on the test charge is given by Q naught E, okay? So if the charge moves an infinitesimal displacement of ds, which is a vector tangent to the path of the particle, then the work done within the particle field system by the electric field on the charge is given by this equation. So W is equal to Fe dot ds, which is equal to Q naught E dot ds. And so this is the work done by the field on the particle. And since this force is conservative, we may write that du, the change in the potential energy of the particle field system, is equal to minus W, okay? And so we have for the change in the potential energy as the particle moves from A to B is equal to minus Q naught integration from A to B E dot ds. And this here is a line integral along the path followed by the particle as it moves from A to B. And as you saw in the videos of mechanics, because the electric force is conservative force, this line integral is independent of the path taken by the particle. So it depends only on the initial and final positions of the particle, okay? So if we divide the potential energy by the test charge Q naught, we get a quantity, this V, known as the electric potential, and this quantity depends only on the source charge producing the field because we divide it by the test charge, so it will eliminate with the test charge here, okay? And so electric potential is a measure of potential energy per unit charge, and its SI units is volts. So 1 volt is equal to 1 joule per coulomb. And so the potential difference between 2 points, A and B, in the field is given by this equation, okay? So ds here refers to the displacement between 2 points in space rather than the displacement of a point charge. And note that as in the case of potential energy, only the change in electric potential is significant. So it does not matter where we choose the reference point, V is equal to 0 or U is equal to 0. The change is what counts, okay? And also note that the change in electric potential between 2 points, or the potential difference between 2 points, depends only on the source charge. But if we want delta U, we must have a system of 2 or more charges, okay? And the change in the potential energy will be associated with the change in the position of these charges relative to one another. So suppose an external agent moves the test charge without changing its kinetic energy. Then the work done by the field on the charge, this one, is equal to the negative of the work done by the external agent causing the displacement, okay? So the work done by the external agent is then equal to plus delta U. So for an arbitrary charge, okay, so any charge, not the test charge, any charge, the W is equal to Q delta V. So this shows that 1 joule of work is needed to move a 1 coulomb charge through a potential difference of 1 volts. Okay? Since also the potential difference is equal to the electric field times distance, it follows that 1 volt is equal to 1 Newton per coulomb times meter, right? And so another another SI unit of the electric field is Newton per coulomb is equal to 1 Newton per coulomb. The unit we found before is equal to also 1 volt per meter. So this shows that the electric field represents the rate of change of the electric potential with respect to position. Um, another unit of energy used in atomic and nuclear physics is the electron volt. Okay, so it is the amount of energy gained or lost by a charge field system when a charge of magnitude of E, so this is equal to E, is moved through a potential difference of 1 volt. So it is equal, 1 electron volt is equal to 1.602 times 10 to the minus 19 coulomb times 1 volt. And this is equal to 1.602 times 10 to the minus 19 joules. Okay. So we will now discuss potential difference in a uniform electric field. So consider a uniform electric field along the negative y direction, and we want to calculate the potential difference between 2 points A and B that are separated by a distance d. So VB minus VA is equal to delta V is equal to minus integration from A to B E dot ds. As you can see, the angle between E and ds is 0, and the field is uniform, so we can put it outside of the integral, and so we get VB minus VA is equal to minus ED. Okay, and because it is negative, this shows that VB is less than VA. Okay, so this means that the electric field lines always point in the direction of decreasing electric potential. So they point in the direction from high potential to low potential, okay? And so the change in the potential, in the electric potential energy of the charge field system when a positive test charge Q naught moves from A to B is equal to minus Q naught ED. So since Q naught is positive, delta U in this case is negative. And so as the positive test charge moves in the direction of the electric field, its potential energy or the potential energy of the charge field system, it will decrease, okay? And since the work is equal to minus W is equal to minus delta U, it follows that the field does positive work on a positive test charge. So when the charge moves in the direction of the electric field, okay? So this means positive work by the field means if the test charge is released from rest, it will experience an electric force Q naught E in the direction of E, and it will accelerate downwards, okay? And it will gain kinetic energy because it is positive work. And this gaining kinetic energy is equal to the decrease in the potential energy of the charge field system, okay? And this is because the electric force is conservative. So any gain in kinetic energy is associated with a decrease in the potential energy of the system and vice versa. So now imagine this test charge is negative, okay? In that case, if we release it from rest, it will accelerate in the direction opposite to the field, okay? This is its natural movement direction, because the electric field always points from the positive charge towards the negative charge. So it will accelerate towards the positive charge. If we wanted to move in the direction of the field, an external agent must apply force and do positive work on it, okay? So now suppose a charged particle moves from A to B in a uniform electric field and the displacement is not parallel but is at some angle with E, theta. So the potential difference of VB minus VA is equal to minus integration from A to B E dot ds, and E is constant, it gets out, and we have minus E dot s. So the change in the potential energy of the charge field system is delta U is equal to Q naught delta V is equal to minus Q naught E dot ds. Okay. And this equation, the equation of VB of delta V shows that all points in a plane, so all points in a plane perpendicular to a uniform electric field are at the same potential. You can show this using the dot product here. You can prove that VB minus VA is equal to VC minus VA, and this means that VB is equal to VC. So this is all points at this surface are at the same potential, and this is known as an equipotential surface. And an equipotential surface is defined as any surface in which all points within the surface have the same electric potential. For a uniform electric field, a family of parallel planes that are perpendicular to the field are equipotential surfaces. So this surface is an equipotential, and this is an equipotential surface. Any surface that is perpendicular to the field is an equipotential surface. So as an example, let's consider the electric field between two parallel plates of opposite charge. So suppose a battery has a potential difference of 12 volts, and suppose that the separation between the plates D is equal to 0.35 centimeters, okay? And if we assume the electric field between the plates to be uniform in both the magnitude and direction, which we can assume if the separation between the plates is small compared to the plate's dimension, then we can use the concept of electric potential to find the electric field. So the electric field is equal to VB minus VA over D, which is equal to 12 volts over D, and this gives an electric field of 3.4 times 10 to the 3 volt per meter. We will later see that the two plates form a parallel plate capacitor. So we will now consider electric potential and potential energy due to point charges. So suppose we have a positive point charge and we want to calculate the potential difference between A and B. So VB minus VA is our minus integration from A to B E dot ds. And in this case, for a point charge, we know that E is equal to KEQ over R square R, which is the radial unit vector, right? Dot ds. And R dot ds is equal to ds cosine theta, and this is equal to dr, right? So dr is equal to ds cosine theta. And so this gives the expression for VB minus VA is equal to KE Q 1 over RB minus 1 over RA. So this shows that the integral between A and B is independent of path and depends only on the radial coordinates RB and RA. And also delta U, which is equal to Q naught delta V, is also independent of path, and this is consistent with the fact that the electric force is a conservative force, okay? So if we choose the reference point at infinity, so let RA go to infinity, then 1 over RA goes to 0, and the potential of a point charge at any point P, let's call it B, is KEQ over R, right? Okay, and if we have more than one point charge, we can use the principle of superposition So V is equal to Ke sigma I Qi over Ri. And so Ri here is the distance from P, the point where we want to evaluate the electric potential, to the charge, the ith charge, okay? So suppose now we have a system of 2-point charges, Q1 and Q2. So, and suppose V2 is the electric potential at point P due to Q2. So this is the distance from Q2 to point P. And we want to bring another charge Q1 from infinity and place it at P. Then the potential energy of the two charge system is equal to Q1 V2, and this gives Ke Q1 Q2 over R12, and R12 is the distance between Q1 and Q2, okay? Um, so if Q1 and Q2 have the same sign, then U is positive, which means an external agent must do positive work to bring Q1 from infinity and place it at P without acceleration. Because the two charges will repel, right? So a positive, the external agent must do positive work to bring them close to each other. If Q1 and Q2 are of opposite sign, then U is negative, and the negative work is done by an external agent to oppose the attractive force between them, okay? So suppose we have this arrangement here and we want to find the potential at P. So the potential at P is equal to Ke Q1 over R1 plus Q2 over R2. And the distance from the 2 microcoulomb charge is 4 meters, and the distance from this charge is 5 meters from Pythagoras theorem, right? And this gives a potential at P equal to minus 2.7 times 10 to the 3 volts. So let's imagine now we bring a third charge, 3 microcoulomb, from infinity and place it at P. And we want to find the change in the potential energy of the system. So if we take the reference point for the potential energy as 0, then the final potential energy is Q3 Vp. So the change in the potential energy is equal to minus 8.1 times 10 to the minus 3 joules. And note that we did not include the potential energy associated with the pair 1 and 2 because we are calculating the change in the potential energy as a third charge is moved from infinity to the system. And the potential energy associated with Q1 and Q2 will not change. So we will now consider obtaining the value of the electric field from the electric potential. So dV is equal to minus E dot ds, and if the electric field is directed along x, then E dot ds is equal to Ex dx, and so Ex is equal to minus dV over dx. And therefore, as we said before, the electric field is a measure of the rate of change with position of the electric potential, okay? So suppose we have an equipotential surface. All these dotted lines are equipotential surfaces. Then dV along the surface is equal to 0 because the electric potential is constant over that surface. So if a test charge undergoes a displacement ds along an equipotential surface, then dV is equal to minus E dot ds is equal to 0 in that case. And this shows that E and is perpendicular to ds. So for this to be 0, the angle between E and ds is 90 degrees. And so equipotential surfaces must always be perpendicular to the electric field lines passing through them, okay? So for a radial electric field, in the case of a charge distribution that has radial symmetry, like this, dV is equal to minus ER dr, right? So ER is equal to minus dV over dr. And if the electric potential is a function of all three coordinates, we have Ex for each coordinate given by these equations, okay? So the figure shows equipotential surfaces of a uniform field from an infinite sheet of charge. Also, it shows the equipotential surfaces of a point charge. So, as you can see, the equipotential surfaces are concentric spheres perpendicular to the field lines. And these dotted lines here are also equipotential surfaces for the electric field of a electric dipole. So we will now consider electric potential due to a continuous charge distribution. So to calculate the electric potential due to a continuous charge distribution, we consider the potential due to a small charge element dq. So the electric potential at point P due to this charge element dq is given by Ke dq over r. So r is the distance from the charge element to the point P. And so the total potential at P from all charge elements is equal to Ke integration dq over r. And note that for this expression, the electric potential is taken to be zero if P is at infinity. We will now consider the electric potential due to a uniformly charged ring. Okay. So consider a ring of radius A and total charge Q. We want to find the electric potential at a point P along the x-axis, which is perpendicular to the plane of the ring. Okay. So from symmetry, all points on the ring are at the same distance to P, right? And so V is equal to Ke integration of dq over r, and because the distance is the same for all dq's, we can put it out of the integration, and we get for V Keq total charge over square root a square plus x square. So let's find the electric field at point P using this expression of V. So Ex is equal to minus dV over dx, and if we solve this, we get Ex is equal to Kex over a square plus x square to the power of 3 over 2. This result agrees with the expression we got before from the direct integration of the electric field. So we will now consider the electric potential of a charged conductor. So we have seen that for a solid conductor in electrostatic equilibrium, the charge resides on the conductor's outer surface. And also we have seen that the electric field just outside the conductor is perpendicular to the surface at each point, and also that the electric field inside the conductor is zero. So now suppose we have 2 points A and B on the surface of the conductor connected by a path. Since E is perpendicular to ds at each point, then we have E dot ds is equal to 0. And this shows that VB is equal to VA, which means that V is constant over the surface, okay? And so the surface of any charged conductor in electrostatic equilibrium is an equipotential surface. So this is an equipotential surface, okay? And also because the electric field is zero inside the conductor, the electric potential is constant everywhere inside the conductor and is equal to the value at the surface, okay, to its value at the surface. And this shows that no work is required to move a charge from inside a charged conductor to its surface, okay? So let's consider, as an example, a solid conducting sphere of radius r and total charge q. So this is a plot of E versus R and V versus R for this sphere, okay? So as you can see, at the surface of a conducting sphere, the potential is equal to here at the surface, when R is equal to R, it's equal to Keq over R, okay? And because the entire sphere is at the same potential, the potential at any point inside the sphere is equal to KEQ over R. So the surface charge density is uniform on the sphere, but if the conductor is non-spherical, as in the shape shown here, so here the surface charge density is uniform, but here the surface charge density is high where the radius of curvature is small, okay? And it is low where the radius of curvature is large. And since the electric field just outside the conductor is proportional to the surface charge density, it follows that the field is very large, can be very large near convex points of small radii of curvature. So we will now consider the example of two connected conducting spheres as shown in this figure, and they are connected by a conducting wire. So if the spheres are in equilibrium, and suppose the charges are Q1 and Q2, and both are uniformly charged, we want to find the ratio of the magnitudes of the electric fields at the surfaces of the spheres, okay? So suppose the spheres are far apart so that the field of one does not affect the distribution of the other, okay? And the conducting wire here ensures that both are at the same potential. So V, the potential of each sphere is equal to KEQ1 over R1 and is equal to KEQ2 over R2. And this gives us this ratio. And the electric field outside of the first conductor is equal to this expression, and for E2 it's equal to this one. And so the ratio E1 over E2 using this equation will give us E1 over E2 is equal to R2 over R1, okay? So even though both spheres are at the same electric potential, the electric field is stronger in the vicinity of the smaller sphere, okay? Which shows that the electric field is large at sharp points, as we said before. So this proves the previous point when we said the electric field, there is a high electric field at small radius of curvature. So even though both spheres are at the same electric potential V, the field is stronger in the vicinity of the smaller sphere. So E2 is larger than E1, okay? And this proves the point we said before, that the electric field is large at small radius of curvature. So it's large at sharp points. And you can see from the equation here that if R2 goes to 0, E2 will go to infinity. So let's now consider a cavity within a conductor that is in electrostatic equilibrium. Suppose there are no charges inside, so the electric field inside the cavity is 0. And note that this field is 0 even if there is an electric field existing outside of the conductor. And we can show this from this equation. So VB minus VA is equal to integration from A to B E dot ds. And A and B are 2 points on the cavity's surface. And therefore, they are at the same potential because the conductor is in electrostatic equilibrium. So VB minus VA is equal to 0, okay? And so this means that this integral here is equal to 0 for all paths connecting the 2 points. And the only way this is possible if E is equal to 0 everywhere inside. So this is possible if E is equal to 0 everywhere inside the cavity. And so a cavity surrounded by a conductor is a field-free region as long as there are no charges inside the cavity, okay? And this is known as shielding. So for example, an electronic device or a room can be surrounded by conducting walls to shield it from external fields, okay? So we will now discuss capacitance. So a capacitor consists of two conductors of any shape of equal and opposite charge, okay? And the potential difference between them is delta V. And to accomplish this, the two neutral conductors are connected to the terminals of a battery. The battery is then disconnected and the charges remain on the conductors, okay? So a capacitor is a way to store charge. So a capacitor stores charge, okay? The potential difference between the two conductors is proportional to the charge on each, okay? It's the same charge, so it's proportional to Q. So the capacitance is defined as Q over delta V, and therefore it's a measure of the amount of charge that can be stored on the capacitor for a certain potential difference. And the SI unit is the farad, so 1 farad is 1 coulomb per volt. In devices, capacitance usually has a range of values in the picofarads or microfarads, okay? And we will see now that capacitance depends on the geometrical configuration of the conductors. So let's consider the parallel plate capacitor, which consists of two parallel plates of equal area A separated by a distance d, and each plate has a charge Q. And the surface charge density is sigma, which is equal to Q over A, okay? So if the distance between the plates, d, is small compared with the plates, we can assume the electric field to be uniform between them and zero elsewhere, okay? The magnitude of the electric field between the plates is given by sigma over epsilon naught, which is equal to Q over epsilon naught A. And the potential difference between the plates is given by ED, okay, because the field is uniform. And so delta V is equal to QD over epsilon naught A. And so the capacitance, which is Q over delta V, is given by this expression, which is epsilon naught A over D. And this shows that for a parallel plate capacitor, the capacitance is proportional to the area A of the plates and is inversely proportional to the distance between them d, okay? So we will now consider the cylindrical capacitor. So suppose we have a cylindrical conductor of radius A and charge Q that is coaxial with a larger cylindrical shell of radius B and charge minus Q. And suppose the length of both cylinders is L, and suppose that L is large compared to either A or B. So we can ignore the edge effects, and the electric field is confined to the region between the cylinders and is perpendicular to their axis, okay? So it's radial like that. And so we have the potential difference between a point here at B and A is equal to this expression. And E here is the electric field in the region between A and B. And if we use the previous result, we obtained for the electric field of a cylinder of a uniform charge per unit length lambda. It was given by 2 Ke lambda over R. So where E is radial, directed radially outward. And also note that the cylindrical shell does not contribute to the field inside here, okay? Because we are only considering the field between them. So this will give us this expression. So we substitute for ER and we get this expression for the potential difference. And since lambda is equal to Q over L, we can get, when we substitute for C, we get this expression. Okay? So we will now consider combination of capacitors. So for parallel combination here, as you can see. But first note that in circuit diagrams, a capacitor is represented by this symbol, and a battery is represented by this symbol, which shows that the positive terminal of a battery is at a higher potential than the negative terminal, and this is represented by a longer line, okay? So if two capacitors are connected in parallel, as shown here, as you can see, the right and left plates of both capacitors are connected to the same battery side, and so the potential difference across both is equal to delta V. It's equal to, so delta V1 is equal to delta V2 and is equal to delta V. And note that Q1 and Q2 represent the maximum charge that can be reached on each capacitor after being connected to the battery. So the total charge Q total stored by the two capacitors is equal to Q1 plus Q2, and this total charge is equal to C equivalent times delta V. And so if we substitute, it is equal to Q1 plus Q2, and we get this expression. And since delta V is equal to delta V1 is equal to delta V2, we have C equivalent is equal to C1 plus C2. And for more than two capacitors, we have this expression. And so you see that the equivalent capacitance is greater than any of the individual capacitors, okay? And this is because when we connect capacitors in parallel, we are actually combining the areas of all the capacitors, which will, as a result, increase the amount of charge stored. So we will now consider series combination. So when a battery is connected to two capacitors in series, so electrons transfer from the left plate of C1 to the right plate of C2, and so the negative charge accumulates on the right plate of C2, and as a result, electrons are forced out from the left plate of C2, which leaves it with a positive charge, and these electrons leaving the left plate of C2 transfer and accumulate on the right plate of C1, okay? And so as a result, the right plates of both C1 and C2, so this plate and this plate, has a negative charge, and the left plates, this one and this one, are left with a positive charge, okay? Plus Q. So therefore, the charges for capacitors connected in series are equal. So Q1 is equal to Q2 and is equal to the total charge Q. The total voltage delta V total is equal to delta V1 plus delta V2, and these are the potential difference across each capacitor. So, and delta V total is equal to Q over C equivalent. And so if we substitute Q over C equivalent, we get here Q1 over C1 plus Q2 over C2, and this gives us this expression for the equivalent capacitance of capacitors in series. And so as you can see, the equivalent capacitor is always less than any of the capacitors in the combination, okay? So as an example, consider the system of capacitors shown. So the unit here is microfarad. So we want to find the equivalent capacitance. So first we reduce the ones in parallel, okay? So they add up. So this is 6 and this is 4, okay? Then we reduce the ones in series. So here in series, which is 1 over C equivalent is equal to 1 over 4 plus 1 over 4, which is half, and this gives equivalence of 2. Same here, it will give 3. And then we add these, and the equivalent capacitance is 5 microfarad. Okay. So we will now consider energy stored in a charged capacitor. So consider a capacitor that is initially uncharged and then we connect it to a battery, and as a result it acquires a charge of Q. Okay. So the electric potential energy stored in a charged capacitor is just equal to the amount of work required to charge the capacitor. Okay. So the amount of work required to charge a capacitor is equal to the potential energy stored in the capacitor. So the amount of work required to charge a capacitor is actually the work required to separate the opposite charges and place them on the different conductors. Okay. So let small q be the charge at an intermediate state during the charging process. So then the work dW done by an external agent to transfer dq from one plate to another is given by this equation. So dW is equal to delta V dq, and delta V is equal at any stage while it's charging is equal to Q over C dq. Okay, and so we integrate W from charge 0 to the final charge of the capacitor, and this gives the work done to separate the charges on the different conductors and place them on the different conductors is Q square over T over 2C. Okay. So suppose we take the reference point U is equal to 0 of the potential energy to be the potential of an uncharged capacitor. Okay, so when the capacitor is uncharged, we take Q is equal to 0. Then we have the energy stored in the capacitor is equal to the work done to separate the charges, and this is equal to Q square over T 2C. And it's if we substitute, we can express it this way or that way. Okay, using the equation for the capacitance, which is so delta V is equal to Q over C. So note that when we calculated the energy stored, we used the model of an external agent that does work on the system. But of course, it is not the charging of a capacitor is not a result of mechanical work done by an external agent to separate the charges, but it is due to the transformation of chemical energy in the battery. But our use of work done by an external agent is justified because the potential energy in a capacitor is a state variable. Okay, so it does not depend on the charge transfer process or the path taken, just like a state variable in thermodynamics, such as internal energy, as we have seen in thermodynamics videos. So the result we obtained for the potential energy stored in a capacitor applies to any capacitor geometry, and also any capacitor has a maximum energy or charge that can be stored. And this is due to electric discharge that will eventually occur between the plates at a sufficiently large value of delta V. Okay. And so a capacitor is labeled by a maximum operating voltage. Okay. So this potential energy of the capacitor is stored in the electric field between the plates. Okay. So for a parallel plate capacitor, the potential difference between the plates is given by ED, and the capacitance is epsilon naught A over D. And the potential energy stored is half epsilon naught AD E square. Okay. So the volume of the space between the plates is equal to AD, and so the energy per unit volume stored in the space between the plates is given, or in that electric field, is given by U over AD. Okay, and this gives an energy density equal to half epsilon naught E square. And this expression for energy density is not only valid for a capacitor, but represents the energy density in any electric field, okay? So we will now consider capacitors with dielectrics. So a dielectric is an insulating material such as paper or glass. So if a dielectric is inserted between the plates of a capacitor, the capacitance will increase. So suppose we have a parallel plate capacitor of charge Q naught and capacitance C naught without a dielectric. And if we use a voltmeter to measure the potential difference between the plates, it will be delta V naught, which is equal to Q naught over C naught. And note here that the circuit is open, so charge cannot flow, right? So now if we insert a dielectric between the plates, the voltmeter reading will decrease by a factor of K. So the new potential difference is less than the potential difference before inserting the dielectric by a factor of K. So because the circuit is open, the charge on the capacitor does not change. So it is still equal to Q naught. And so the new capacitance after inserting the dielectric is Q naught over delta V, which is equal to Q naught over delta V naught over K, which is equal to Kc naught. And so this shows the capacitance increased by a factor of K if the dielectric completely fills the region between the plates, okay? And the energy stored in the capacitor before inserting the dielectric is Q naught square over 2 C naught. And after inserting the dielectric, it is Q naught square over 2C. And if we substitute for C, it gives U naught over K. And since K is less than 1, then the final energy stored in the capacitor is less than the original, and this decrease can be accounted for by the negative work done by an external agent to place the dielectric and keep it from not accelerating. Okay. If the dielectric, in the case if the dielectric is inserted while the capacitor is connected to a battery and held at a certain potential difference, okay, in that case the charge will increase by a factor of K, and this charge is transferred through the wires, and so the capacitance still will increase by a factor of K, okay. Because here, instead of Q naught being constant, in the case it is not connected to a battery, and the potential difference change, the capacitance increase. If we insert the dielectric while it is connected to a battery, then delta V is held constant. So delta V is equal to delta V naught. And what changes is the charge from Q naught to Q. And this still will increase the capacitance by K. Okay. So for a parallel plate capacitor, we have C is equal to K epsilon naught A over D. And note that each capacitor has a maximum operating voltage, and this represents the voltage before discharge occurs, okay? And it depends on the maximum electric field that a dielectric can withstand before its insulating properties breaks down and it begins to conduct, okay? So this maximum electric field of a dielectric is known as the dielectric strength, and for dry air is given by 3 times 10 to the power 6 volt per meter, okay? And most insulators have dielectric strengths greater than that of air. And so inserting a dielectric has the advantage of increasing the capacitance, increasing the maximum operating voltage, and also providing mechanical support that allows the distance between the plates to be decreased further, because if we decrease D, the capacitance also will increase. And the origin of the effect of the dielectric on capacitance is due to the polarization of molecules. So as you can see in the figure, in the absence of an electric field, the polarized molecules of the dielectric are randomly oriented like that, okay? And if the dielectric is placed in the electric field between two charged plates of the capacitor, um, the polarized molecules, as you can see, align themselves parallel to the field. So as you can see, the field produced by the plates is E naught, so the molecules orient themselves with E naught. And the orientation of the molecules with the field, as you can see here, when they orient with the field, they produce a layer of negative charge here at this side and a layer of positive charge on the opposite side. In the middle, the charges cancel out. And as you can see, the polarity of the layers is opposite to the plate's polarity, right? And these two layers, they will induce an additional electric field, E induced, directed opposite to the electric field of the capacitor. So E naught is directed this way and E induced is the opposite way. And therefore the total electric field inside the capacitor is reduced, and as a result the voltage is reduced due to this introduction of the dielectric into the capacitor. Okay, so this means that the charge Q is now stored in the capacitor at a lower potential difference, which will increase the capacitance. So there are many types of capacitors. Commercial capacitors come in different forms and many are built into integrated circuit chips. A tubular capacitor, for example, is made using layers of metal foil interlaced with a dielectric and rolled into a cylinder. Another capacitor type consists of parallel plates separated by an insulating oil. There is also the electrolytic capacitor used to store large amount of charge at low voltages, and it consists of a metal foil in an electrolyte, which is a solution that conducts electricity through the motion of ions in the solution. And when a voltage is applied, a thin layer of metal oxide, which is an insulator, is formed on the foil, which serves as the dielectric that will increase the capacitance. So as usual, I included some solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.